So welcome to this Monday webinar, where we are so lucky to have Paul Schneider from BASF in Germany, who is actually doing a joint PhD with us here at the University of Copenhagen. And he's been working a lot lately with different ways of speeding up the very slow Parafact2 algorithm. And he's going to talk about some of his work on that. So, Paul, please go ahead.
Yes. Thank you, Rasmus, for the kind introduction. And yeah, as Rasmus said, my perspective is a bit the one from a PhD, but also from someone who has worked in chemical industry. So yeah, just that you are aware that I'm a little bit biased maybe. But today I would like to talk about shift-invariant trilinearity and shift-invariant soft trilinearity, which are two chemometric methods that can be used to model GCMS data. And I will present work that I did together with Rasmus Bro and Neil, as part of my joint PhD, as Rasmus just mentioned. So I will, throughout the talk, I will stick to this abbreviation, SIT for shift-invariant trilinearity and SIST for the other one, just because the words are too complicated. Okay, so I would actually like to start with a short warm-up. I don't know if we are enough people here to do that, because I prepared a Menti poll just to get to know you as an audience a bit better. I think we will give it a try, and I hope that all of you will participate. And then I will dive into the actual chemometric stuff. I first want to motivate why I think it is important to think about advanced data analysis, also or especially related to GCMS. I will then talk about the state of the art for modeling shifted trilinear data before I go into the details of the algorithmic framework for SIT. Then I show some results on real data and also show where SIT actually fails to then move on to SIST, which is a bit, gives a bit more flexibility in modeling GCMS data. I have planned enough time to have some questions in the end, and I hope there will be some. And I would also very much appreciate if you take 1 or 2 minutes to give me a feedback also via Menti, so that I have the chance to learn and improve. But let's get started. And yeah, I hope you are familiar with Menti. If not, it's also not a problem. You just have to take out your smartphone and scan this QR code. Then you will be forwarded to a website where you have to type in this Menti code, and then you should see the first question, which is, are you working with GCMS data? So I will just switch to Menti. The QR code is also on this page and the code, so don't worry if you could not scan it by now. So, and there we are. Here's the QR code, and up here is the code. And I see we have 4 people. That's great. I hope we can get to 5.
But we just stop when we reach the last questions. Oh.
Okay, maybe 4 is all we get. Then let's see. Let's see what the results are. So, oh, there are 5. That's amazing. So we have 3 people of us working with GCMS data. That is very nice. I hope this will be useful for you, and for the people who not work with GCMS. I hope you have some background in analytical chemistry, know what GCMS stands for. It's gas chromatography coupled mass spectrometry, and I hope you can see how the methods I will talk about can also extend to other applications where you have a similar data structure. Okay, let's see how, yeah, so I have to spend a lot of time for data analysis. I'm particularly curious how you would agree with that. Okay, mostly the people agreed. To be honest, I hope that someone would strongly disagree, because then I could ask him for his smart way to be more efficient. But yeah, I would also say data analysis eats up a lot of time, but is also extremely important. So let's see what kind of tools we have. Okay, so that's really great. We have a variety of tools. I'm happy that someone wrote Paradise, and I'm curious, maybe in the question and the Q&A session, how the people using different tools, what their experiences are. So thank you very much. And then I go back to the slides. And let me first of all try to answer the question why I think we should care about advanced data analysis. And I brought here this small example of a GCMS measurement, and we see yeah, a small interval from a larger data set, and here are different total ion chromatograms displayed. And the question is if this is actually important information. And I hope you all agree that we can see that in one sample we have some small peaks here, but the rest looks pretty much like baseline. So if you do manual peak integration and you reached minute 37, I'm quite sure that yeah, you are too tired to really think about if these baselines contain chemical information or not. But indeed, we actually have very, very nice chemical information that is hidden here, and not only in the one sample, but actually in all of the samples. I used here the Perfect 2 decomposition that is implemented in the Paradise software to remove the baseline components and to deconvolute these overlapping peaks. Because we can see that the green and the blue peaks, they are a bit overlapped. But we can also extract the cleaned up mass spectra to actually identify those analytes. So I think we should care about advanced data analysis because it gives us more information, let us allow to extract more information from the raw data that we acquired, and which very often is not really cheap to acquire. And I just try to give a rather generic workflow of the analytical process that I know from my work in chemical industry. And usually we have the situation that we get samples from R&D and from production, and then there is some sort of sample preparation, and finally we perform analytical measurements. I will stick to GCMS as the analytical platform throughout the talk. And by acquiring this raw data, or before acquiring the raw data, we actually have to develop methods. We have to buy rather expensive equipment. So the data that we acquire is expensive. But the raw data in itself has not a lot of value for us. But what we are more interested in is actually this peak table that summarizes the chemical identities of all the analytes and also the concentration of the analytes across the samples. And this peak table is so important because we use it to make decisions. So we want to decide if we can release a certain batch, or we want to decide if a molecule A is worth developing further, or we should take a molecule B. And also in academia, based on this peak table, this is extracted chemical information. We start developing hypotheses about metabolic pathways or whatever. So there is a lot of, this peak table is very important. And also what we may want to do is to develop downstreaming machine learning methods to make predictions about even more complicated properties of our formulations or chemical products to, for instance, know how they would perform in a given application. And also for that, it is just important to have this peak table as complete as possible. But the problem is that we don't have infinite time, so we have to come up with ideas and tools how we can get this maximum of information out of the raw data without spending too much time. And I'm sure you have seen this scheme maybe from a digitalization presentation. So we have this transition from raw data to information, and that is actually where we get value out of the data, because information we can then convert into knowledge using our intelligence or maybe also artificial intelligence. And my claim is that we have to become better at extracting information, because in many industries we have to face increasing regulatory requirements. We have to deal with more complex raw materials if we think about closed loop recycling. We also want to study more complex, maybe biological reaction systems. And at the same time, we want to become faster in R&D. So we want to predict how does a certain chemical product perform in a given application. So that's my view on why it is important to think about advanced data analysis. And one tool that I would encourage you to try out is Paradise. This is software that actually makes at least GCMS data analysis a lot easier. And the methods I will talk about throughout the talk are also implemented in this software. You can give it a try by just going to the UCPH Chemometrics homepage, download it, and just start playing with your data. And if you run into problems or have questions, then I'm sure you can reach out to Rasmus, or there is actually also a lot of good supporting information and tutorials. But let's get to the chemometrics part of this talk, and I will talk about methods that are suited for modeling shifted trilinear data. So I think a natural first question is to ask what is actually shifted trilinear data? So where can we find it? And I would like to start with looking at not shifted trilinear data, or simply trilinear data. And let's assume we have here measured a very simple GCMS data set consisting of 4 samples. And we have measured 3 different mass channels only. And in our retention time window, we have 2 peaks that are eluting. Now we can look at this data from 2 different angles, or probably also more, but I stick to 2. So we have either this 3-way structure or this tensorial data structure. And if we unfold the data in this way, then we get a very long spreadsheet. So you can see that here. In my upper example, all the peaks come exactly always at the same retention time, so we don't have any shifts here. And these kind of data we can easily model with Parafec or with trilinearity constrained MCR, which is basically the same, just implemented in a different way. So, and our latent variable structure, so the result that we get from the model is that we get 3 factor matrices. One of them captures the pure mass spectra. The other one captures the elution profiles that are assumed to be constant across all the samples. And since we don't have any shift here, that is a valid assumption. And then we have the peak areas here in this third factor matrix. Unfortunately, when we deal with chromatography, we have to deal with shifts because, yeah, we can't really keep all the chromatographic and experimental conditions perfectly constant across a lot of measurements. So we very often have to face retention time shifts. And that is displayed here in the lower visualization. And for these data structures, we have to use a bit more complicated models, such as Perfect 2 or MCR with a flexible trilinearity constraint. And the difference between now the Perfect and the Perfect 2 is that we do not assume that one elution profile per analyte is constant across all the samples, but we rather model the elution profiles kind of individually for all the samples, but we impose constraints on how the elution profiles are allowed to behave. So we can model shift, but they have to stick to a certain behavior, so to say. And the lower case is exactly the case of shifted trilinear data. And now I would like to have a look a bit more in detail on the 2 models that are commonly used for modeling this kind of data. So on the one hand side, we have the Perfect 2 model, and this relationship that we want to have between the elution profiles is that they have to have constant cross products across the samples. So the cross products of these elution profiles must be constant across the samples. And yeah, actually I lied on the previous page when I said that that this type of shift can be modeled with Perfect 2. So this peak inversion strictly violates the cross product constraint. Luckily, it's nothing that very often happens in GCMS, or I have to say I never faced this, but I learned that this can happen in liquid chromatography, for instance. But why do we impose this constraint? It is simply to make sure that we get a unique solution so that we avoid rotational ambiguity and with that uncertainty in our estimated elution profiles and mass spectra. The good thing is that we can put constraints in all of the modes. When I speak of modes, I mean the retention time mode or the mass channels or the samples. So we can say that all the elution profiles should be non-negative. And that was not possible with the Perfect 2 ALS algorithm, but now more recent Perfect 2 algorithms actually allow for constraints in all modes. However, the algorithm is considered to be quite complex and tends to be slow, at least compared to Perfect. Now, let's have a look at the MCR with flexible trilinearity. And here, the difference to MCR with normal trilinearity is that the estimated elution profiles are synchronized. And I hope you bear with me. I will explain in a second what that means in more detail. But applying this trick, we actually also get a unique solution here. And the good thing about this MCR trilinearity framework is that we actually can apply constraints not only on all the modes, but also component-wise. So for instance, I can say that I want these yellow elution profiles to be non-negative, and I can require that the blue ones are non-negative and unimodal. So that is a bit more flexibility that I gain in this framework. However, the MCR with flexible trilinearity that was published last year needs for the synchronization step some sort of criterion. And that brings me to the next page, and actually to the algorithmic framework of SIT, where I now want to explain a bit better what actually this trilinearity framework is and what this synchronization step is. So again, we start with the example of the shifted trilinear data, and we look at it in this unfolded data structure. And now we can just simply do in the first step an MCR decomposition, and what we get are two factor matrices. One factor matrix, matrix V, contains the concatenated elution profiles, and the other one contains the mass spectra. And now when we apply this trilinearity constraint, then we take out the first column of this matrix V, which is the first vector of concatenated elution profiles. Then we reshape it to obtain a matrix that is of size, retention times samples. And now we synchronize these elution profiles, for instance, so that the peak maximum for all the profiles occurs at the same position. Now, I hope you can see that this is a rank 1 system, and I can do a one-component PCA model on that to get a very good approximation. And this is actually the trilinearity constraint, that I'm able to reconstruct this matrix via a one-component PCA model. So I do that, and I shift back, and I can do that because I've just stored the values of the initial peak positions. I reshape it, and then I move on to the next vector of concatenated elution profiles. Now, what we did with the SIT algorithm was to look at this synchronization step. And we don't do it by aligning on the peak maximum, but what we rather do is that we perform a domain transfer. So we move the time domain signal to the frequency domain using the discrete Fourier transform. And here on the right-hand side, it's shown what that does to the data and why it is a nice thing. So here we have the shifted time domain signals. And if we perform the discrete Fourier transform using the FFT algorithm, then what we get is a signal in frequency domain that is called amplitude spectrum. And what you can see is that these amplitude spectra, they are all perfectly aligned. And the reason is that we actually have all the shift information stored in the phase spectra. So we can separate our frequency information from the shift information. And this is very nice, because now we can do the one component PCA reconstruction on this matrix of amplitude spectra. And then we can simply go back to our shifted time domain signals by applying the inverse discrete Fourier transform using our approximated amplitude spectra together with the phase spectra. Now, what we saw in comparison to the perfect 2 algorithms, the latest one that we use in Paradise, is that we are with this method 20 to 60 times faster. We also saw that we tend to get better factor resolution in low signal to noise domains. And with that, I mean, we have a very huge baseline and a very tiny peak under it. And the general advantage that I've mentioned earlier is that in this trilinearity framework, in theory, we can put different constraints on the individual factors. We have tested it on GCMS data to make sure it actually works nicely. And we also have received feedback from scientists using it on different data. And they were also quite happy with the performance. Okay, but now let's have a look on some of the results for real data. And here I just have the example I showed you at the very beginning. So here we have the tick profiles. And if we now decompose these tick profiles using a 4-component SID model and the 4-component perfect 2 flexible coupling model, then we see that we don't get the same results. Because here for the SID model, we have a very flat baseline. Whereas for the perfect 2 flexible coupling, you see that we have this a little bit weird inverse peak shape. And we also see that the elution profiles of this peak are a lot larger than they are here. And the reason is that a 4-component model is not enough for the perfect 2 flexible coupling to perfectly unmix these two signals. So we also see in the mass, in the estimated mass spectra, for instance, that we still have contributions from the baseline in there. So that leads to wrong peak areas in that case, and also not perfectly cleaned up mass spectra. The good thing is that by taking more components, we can actually fix that. So an 8-component model of this interval modeled with perfect 2 flexible coupling looks exactly the same for the analytes as the 4-component solution of SID. But the important thing from an algorithmic point of view is that SID tends to be more parsimonious, so to extract the same amount of information using fewer latent variables. Okay, so far we have only talked about shift. And here in the upper part of this slide, I show you what I can do to a time domain signal without having any impact on the amplitude spectrum. So I can translate it across the time axis, that is just shift. A funny thing is that I can also mirror the signal and I will still get the same amplitude spectrum. But I run into troubles when I try to broaden the time domain signal. So if I have a broader peak, and peak broadening is something that can also occur in chromatography, then I end up having a different frequency or a different amplitude spectrum. This is because a broader signal requires less of the high frequencies to get reconstructed. So a broader peak in my time domain signal will look thinner in the frequency domain. And the thing we can conduct from that is that shift-invariant trilinearity will only work when we don't change the frequency distribution of our time domain signal. And I have also a real-world example where SID unfortunately fails. So this is a slightly more difficult interval that I show here. It's also ticks. And I modeled these two data sets with I think with 5 components. And so from the first look, we would say everything is good because we find 4 peaks in total for both methods. It's this small one here, then the red one here. We have a green one under the big blue one. So 4 in total. And the same here, we have this small one. We have here the blue elution profiles. Then here we have this light red and then the normal large red peak. But if we look more in detail on this large peak, then we can see that SID actually has troubles to model this peak shape in a good way. So here with perfect 2 flexible coupling, we can see that the peak shapes are modeled very nicely. And you can also see that here we have more a Gaussian type of signal, and the higher the concentration gets, the more this peak gets skewed to the side. And this is something where the frequency distribution changes, and therefore SID fails. And we can see this also in the residuals. They look kind of weird for SID and are also significantly larger than for perfect 2 flexible coupling. And yeah, this is something where we have to find a solution. And the good thing is that we think we have a fix for that. Because if you look at this example of the broadened time domain signal, then you can see this may not be a rank 1 system, so we can't approximate that well with one principal component, but we can do it with 2 principal components. And the simple extension to the SID algorithm that we propose is to actually perform a rank analysis on the elution profiles to determine the number of principal components that I need to reconstruct my amplitude spectra very accurately. And just to put that into context, what you normally would do, or an alternative way of dealing with this problem, is to go to mixed bilinear trilinear models. So you would say, okay, this interval does not behave like a shifted trilinear thing, and therefore I model it as a bilinear factor. But yeah, maybe the problem is that I give a lot more flexibility than I actually need, because you can see that if I have here in my amplitude spectra, if I have full rank, then I have the case of a bilinear factor. But I can also see here that this is not full rank. This is rank 2. So why not use just 2 principal components and restrict the model just to the flexibility that it really needs? So what we think that we propose with this approach is a control knob that allows you to actually, or that allows the algorithm to find the flexibility that is really required to model a set of elution profiles. And yeah, on the other hand side, you can also see that if we have a rank 1 system, then this just simply becomes SID again. Okay, and the good thing is that it actually works. So here is now the SIST example compared to the perfect 2 flexible coupling. And we can see that it actually provides the same results. Now, what we may have to be concerned with is that now we allowed the model to be more flexible if it is required, but we still hope that the model behaves trilinear or models data as shifted trilinear when the data is actually shifted trilinear. And so we go back to the very first example that I've shown, where SID did a better job than perfect to flexible coupling. And we can see that SIST in this case provides the same result as SID, which is nice. So it behaves more flexible when it is required, but it is like SID when the data is actually shifted trilinear. So yeah, to summarize it, SIST preserves the desirable properties of SID, but extends the SID to model also data that is not ideally shifted trilinear. Okay, and to summarize my talk, SID as an alternative to Perfect 2 provides a significant speed up, which is nice and allows us to calculate more models and to go a bit faster through the data, see to get a first impression. So I think it's always nice when algorithms are faster. It also tends to need fewer factors than Perfect 2 flexible coupling, but actually it's also the Perfect 2 ALS to extract the same amount of information. Now, SIST can model shifted trilinear data even if the elution profiles are not perfectly the same across a set of samples. And yeah, I hope I could show that SID and SIST are especially useful for modeling GCMS data. And SID is already implemented in Paradise. And I hope, or we will see that SIST may become part of Paradise in a future version. Okay, and with that, I would like to thank you all for your attention, and I think we have some time for a Q&A.
Excellent. Thank you so much, Paul. Are you sure that SID is actually in the currently public version? It's going to be in the next one, but
I think it is. I think SID is in the public version.
okay. Yeah, okay, then I think it may actually just be there cryptically because
Okay,
it's
yeah, that could be.
method number 5 and you have to, or 6, and you have to know that.
Yeah, no, that's true. Yeah, it is for advanced users, you could say.
Yeah, but in the next version, when we update, it's going to be a little bit more user friendly.
Yes.
So, okay, nice, very nice. There's a question from Paul. No, sorry, from you.
Yeah, thank you, Neil. I also want to say thank you to Rasmus and Neil actually, because it was a lot of fun to work on that topic, and yeah, I think it really there have been really great discussions that brought up these methods.
Yeah, but he's asking about how many PCs were used in the SIST example.
Okay, so the idea is actually to not manually select the number of principal components, but to use some way of or some sort of principal component number selection method. That was a bit cryptic, but to use some sort of criterion to define the number of principal components that you need algorithmically. So it's not me defining that a priori, but the algorithm should select the number of principal components that it needs to reconstruct the elution profiles. I can also go back to the slides to make it maybe a bit more clear what I mean. So for instance, I mean, in this example here of the elution profiles, I only have peak broadening. Yeah, I have two peaks that have essentially the same shape. And then I have one peak that is broader. And to model that, I need two principal components because I need one principal component that kind of describes the peak shape, the mean peak shape of these three. And then I need one principal component that stretches or compresses this mean peak shape to fit to actually fit the different peak width. But the idea is that also in more complicated examples, so for instance, like here where here where I couldn't tell you how many principal components I need to model that the algorithm also finds the right flexibility to model those kinds of elution profiles. And it seems to work. I mean, there are some tricks with the implementation, but yeah.
So are you saying that we don't need sit because we can just run syst always?
Yeah, I think actually that would be a good choice. I mean, there is a small trade-off because syst is a bit slower because we have to do the rank analysis in the algorithm, and if we do the rank analysis too early, so if we start doing the rank analysis at a point where the algorithm has not really converged, then the convergence time gets longer because you can imagine if you start with random starting values, then the algorithm needs a time to actually get good first approximations of the elution profiles. And until then, the rank of these matrices will vary a lot.
Yeah.
So
it's less straightforward, the algorithm, you can say.
Yes, yeah, exactly. So I think I would use sit first, and then for the intervals where the residuals look strange, I would rerun it with syst. That yeah.
Neil is asking how you choose the number of principal components.
Yes, actually Neil also gave the correct answer himself because I use the variance captured exactly, yeah.
Okay.
And I'm happy. I'm actually happy for suggestions if there is a more clever way. But I felt like it would make sense to aim for a certain level of accuracy in the reconstruction that I could define with variance explained. So let's say I want to have my amplitude spectra reconstructed by 99% or 99.5.
But you know what? Then maybe it makes sense to use the absolute instead of the percentage, because you can actually relate it to the the noise in the data.
Ah, okay.
And if you use percentage variance, then that's a very different criterion for a small peak than for a big peak. You know.
Okay. Yeah.
So,
That's a very nice idea. Yeah.
I mean, conceptually, it's actually even simple to measure what is the noise level, and
Yeah.
then use something related to that as a criterion. Like 3 times above the standard deviation of the baseline or something. Could be.
I think it's definitely something I would try out. Yeah.
Now, I like the presentation very much, and it seems like we can just throw away parafact 2 and flexible coupling. So would there be any scenarios where you don't want to use SID or SIS?
Well, actually, I mean, so perfect to flexible coupling. So working with perfect to flexible coupling and SID actually showed me that SID has its deficiencies. So I think perfect to flexible coupling. We have worked with that on really a lot of different data sets. We are very sure about how it works. And I think, yeah, I would keep it until we are that certain about cyst. So that's maybe my answer. But yeah, I think the two methods look quite promising, and yeah, I think it's now really time to try it out more extensively and see where it still fails. Yeah.